everybody. So today we are going to talk about Markov chains. So this is basically what has happened is you have the option with Sitsikalis's Markov chain 1. So as promised, I am making my own versions of this. So we are going to talk about what is called as Markov chain. Okay, so this is a very intuitive, easy concept, but the thing is, if you don't think about it rightly, you may get confused in the notation. Okay, so my suggestion to you is to approach it with the mindset that this is a concept that is easy to grasp. It's a concept that you have studied always, and it's a concept that is very natural. Alright, so to really understand this, I think the best way to think about it is to look at a simple physics problem that you would have seen in your class 12th or class 11th or perhaps even earlier. So you might have seen this equation v is equal to u plus at, right? So u is the initial velocity, okay, a is the acceleration, and t is the time elapsed. Okay, so what you are doing by this is like, given the initial velocity or the initial state, okay, what you are looking at is at time t, what is the v, which is the final velocity, right? Final velocity at time t. Okay, so initial velocity at time equal to 0. So something like this you would have seen, and Markov chain is also exactly like this. Okay, so the only difference is there is something called as a state, okay, and this is like a law governing it. So similarly there is a what is called as transition probabilities. Okay, so just like you have this equation, transition probability defines the transitions, and the only additional thing is there is some randomness involved. Okay, so this is actually this is how Markov chain will look like. Okay, so what I wrote here is a example of physical system, right? Physical problem. Okay, let's say physical system, and Markov chain is an example where there is randomness involved. In fact, Markov chain is also what is called as a stochastic process. Okay, so this stochastic process you have already seen when you saw Bernoulli process, when you saw Poisson process and all. Okay, so Markov chain is also like that. Okay, so you will soon see why I am saying all of these things, and it will be quite clear what is going on. All right, so what we will do now is to look at an example to start with. All right. Okay, so now let us look at a checkout counter model. So think of like a railway counter. So there is a railway ticket counter. Okay, so what that means is you have a counter where you are observing the counter at very small time intervals. Okay, so you are looking at this counter and you are looking if there are any customers arriving. Okay, and you are looking at a very small interval. So remember how we thought about this in the Bernoulli process. So same way, what you are looking at is a very small interval. In the small interval, the entire time axis has been divided into very small intervals, and at each interval, the interval is so small that there can be either one arrival or there will be no arrivals. Okay, so you look at a railway ticket counter, there is a queue there. Okay, so if there are already people waiting in the queue, then if the new person comes, he goes and joins at the end of the queue. So this is the new person. Okay, and in this very small interval, there could be one person who is leaving. Okay, so this is the model. Now, is this a reasonable model? Yes, it is a reasonable model. We start simple, right? So if you remember how we did in the case of Bernoulli process, we also started with something similar, right? So this also we are looking at as a checkout counter model that we are studying here is to motivate the idea of Markov chain. Alright, so what we are looking at is a railway ticket counter. Okay, there is a queue and we are looking at very small intervals, and in each small interval there could be one person coming in or there could be one person leaving. Okay, but there cannot be two persons coming in or there cannot be two persons leaving. Okay, so it can happen that one person enters the queue at the same time that in that small interval one person leaves the queue. That is possible, but you cannot have two of them. So what you have done is, since you are divided into time interval, you start labeling each time interval as 0. So this is the time interval, suppose. So this is not the queue, but okay, let's say this is the queue. So this is the number of people standing in the queue. New person comes, he joins at the end of the queue. Okay, the time, if you want to look at the time axis, so this is time. Okay, time axis. So you can divide the time axis into very, very small intervals like this. Okay, let's say this is 0.1 second intervals, something like that. And you can name these time slots as 0, 1, 2, 3, 4, 5, 6, 7 and all. Okay, so in time 7, it doesn't mean there are 7 people. Please don't get confused with this. So this 7 means at time interval 7, what is the state of the queue? That is what we are looking at, right? So state here represents the number of customers at time n. Okay, and as I described earlier, the customer arrival we will think of as Bernoulli, same as Bernoulli process with the probability of P arriving. And when you know that in a Bernoulli process, time between two people coming in is geometric. All right. So, and similarly, customers, once they are able to finish their transaction, they leave with probability Q. So what you can think of, there are various ways in which you can think of. You can think of like there is a synchronization. There is a synchronization. Okay, so there is, you can think of this like people, there is a person with at every time somebody does a coin toss with probability P. If it turns out head, a new customer arrives. At the same time, in the same time slot, there is one more person who is doing a coin toss with probability Q, and if a head comes in, one customer goes away if there were some customers. Okay, that is an important thing. All right, and so one of the things is the state. What is the state of the queue? How many people are there in the queue? Okay, so that represents the state of the system. So now you can think of this states in this manner. So this being, there are no people in the queue. This means there are 1 people in the queue, 2 people in the queue, 3 people in the queue, and so on. Okay, so if there are nobody in the queue, when does it remain in the same state? That means there are no customer arrivals. This happens with probability 1 minus P. Okay, P represents the probability that a customer arrives. Okay, so when there are nobody in the queue, there is no customer service, right? So it cannot be that you can go from here to -1. That's not possible. The person who is at the checkout counter, the railway ticket issuing person, he or she cannot do anything until there is a customer. Okay, so this is the state. So now if there is a customer coming in, the probability that happens is that in the time interval, whatever this time interval is, in the time interval somebody has done a coin toss, okay, and that turned out to be head. So one customer arrives. Okay, so now given that there is one customer being serviced, okay, when does it become to 0? So that means that customer has been already serviced. So that means that task has been done. So this happens with probability Q. That customer leaves with probability Q. Okay. Now this state. So this is the case that from one customer it remains in one customer. So how that can happen? Okay, so that is the next thing. You have to think carefully about this. So as I was telling, we have to be very careful when we think about this. So you can remain in state 1 if there is one customer arriving, okay, and one customer departing. Okay, so that will keep in state 1. Or it can also be that there is no customer arrival and no customer departure. Okay, and similarly over here from 1 to 2, when does that happen? You have a customer arrival but you have no customer departure. Okay, and likewise in this one, from 2 to 1, it will happen if you have a customer departure but no corresponding customer arrival. Okay, so this is the way it happens. Okay, now the railway counter, let's say the capacity of queue is 10. Okay, after 10 there is no space and this is what the system is. So you can have a system like this. So the transition probabilities change a little bit from here and here. See, here at this point there is no 1 minus q because it doesn't matter. I mean, you cannot at state 0 there cannot be a customer departure. Okay, So likewise, from 1 to 0, of course there is a mistake here, you see. So from 1 to 0 this can happen. So from 1 to 0 you can have that there is a customer departure, but there has to be no customer arrivals. Okay, so just be careful when you write these probabilities. Okay, but it's easy to understand how this is happening. I hope it is clear to everybody. Okay, this number is not, this number and this number look little different because at state 0 you cannot have a customer departure. Okay, customer service doesn't happen, so it cannot depart. Okay, so this is the called as a state, the number of customers at time n. Okay, so now don't get confused with the time n here, and if there is a n here, right? Suppose n equal to 9 and this 9, it doesn't mean that at time n equal to 9 it is here. Okay, this and this are having no specific connection. Alright, it is possible that at time n equal to 9 there could be 9 customers. It's possible. Okay, but this Markov chain is just representing the states and how it can go from one state to another, and time is a different thing. Alright, so this here, for example, this is the queue length. Okay, this is a different thing, and this time dividing into different units is a different thing. So you have to be careful in these aspects. So once you get these ideas clear, it should be clear for you what's going on. Okay, so now in this example, the number of states can belong to one of these, right? It can be 0, 1, 2, all the way till 10. So there is no capacity beyond 10. So this represents the state. All right. And then furthermore, yeah, so this is how the system is, and this is a particular system, and the transition, right, from some state to another state depends upon what is the value of the current state. What do I mean by that? Okay, if at some time, okay, so say like, let's say xn is equal to 0. Okay, at this time you cannot go to, for example, from xn equal to 0, you cannot go transition to xn plus 1 equal to 5. That's not possible, because from 0 you can only go to 1. Okay, or you can remain in 0. Okay, but you can never go into xn equal to 5. So what we are trying to say is that function, so I meant next state, okay, xn plus 1. So function, the function that, so next state, okay, so next state, okay, is going to be some kind of a function of the current state. Okay, so it depends on the current state. So that is an important thing in the Markov chain. Of course, plus randomness. So comma, let's say some randomness. Okay, so that's how you have to think about this system. Okay, if you want to start abstracting, let's do that. Okay, so let's try to abstract this problem a little bit. So what you have in a Markov chain is that you have states. Okay, so you have these states. Let's say this is state 1, 2, 3, okay, for something like 4, 5, and then let's say this is a state I, okay, then some other state J, something like this. Alright, and then from a given state you can go to the next state with some probability. Okay, and that depends upon what state you are, as I told you here, right? The next state depends on the current state. Okay, so that is represented by a probability, and we write that as P31. So what is P31? P31 is the probability that next state, okay, is 1 given that the current state is 3. Okay, so likewise we can write all of these probabilities. Okay, so let's write that. So this is P32, okay, then this is P34, all right, and then this is P35, and then P3I, okay, then this is, let's say, P3J, and we can also have a loop like this. That means from J you are going back to J. This will be PJJ. Okay, and what is the idea? Pij, what it means by definition, this is probability that xn is equal to I, xn plus 1 is equal to I, given that xn is equal to j. Okay, now if you really think about it, okay, there is a clear, we have made some very strong assumption. Okay, so what is the assumption? We are saying that transition to state J only depends upon current state I. Okay, it only depends on current state I and not upon how the Markov chain got to I. Okay, so that is an important property called as a Markov property. Okay, so what does that mean in terms of the notation that we have learned in probability theory? What we are saying is probability Pij is equal to, by definition, probability that xn plus 1 is equal to j given xn is equal to I, and it does not depend upon anything else. So what that means is this is also equal to, it is conditionally independent upon how it got there. So let us say xn plus 1 given j, okay, given xn equal to I, okay, xn minus 1 is equal to some other state, let us say I1, and xn minus 2 is I2, and so on. So if this was, suppose this was the state, it started from a state I0 and then it transitioned into various states, and then at xn it got to I, and from there it got to j. This entire probability always remain as Pij for all possible values of I, I1, I2. It doesn't matter how you got to state I, okay, but the probability that from that I to some other j, that remains same no matter how you got to I. Okay, so this is called as the Markov property. Alright. So another way to think about it is the transition to state j from state I does not depend upon how the past, how it got to I. Okay, so that's an important property called as a Markov property. See, this Markov property is not something very new, right? So if you go all the way back to that initial physical system example I gave you, so v is equal to u plus at, right? So given that the velocity at time 0 is u, okay, and the acceleration at that time is kept fixed at a, at time t the velocity v is clearly known. It does not depend upon how the object state was before time t equal to 0. At time t equal to 0, what is the velocity? That is the only thing that is important. Okay, so it's not very new. So don't get very confused. Okay, so whatever I am saying is that this idea that it depends only on the current state, it is not new. Okay, so same thing is happening even in Markov chain. All right. So now, in order to really specify a Markov chain, so we did an example of the checkout counter, right? What we identified is the state is the number of customers. We also understood that since the time interval is extremely small, there can be only one customer coming in or one customer can leave. Okay, we further observed that at state 0 you cannot have customer leaving because there is nobody to leave. Okay, and then we wrote all these probabilities. Okay, so then we also saw what's the Markov property. So if you really truly want to specify the model, what are the things that you need to specify? So what are the model specifications? So that is the next question, and it is easy. What you do, you first identify the states. Okay, identify the states. So the states in the checkout counter example is the number of people, and you said okay, the capacity is 10, you cannot have more than 10. So that is the first step. All right, then you look at what are the state transitions. Okay, so what this means in the context of the previous example, we said that the probability, the time interval is so small that from state 0 you cannot have two customers. There cannot be any jump from 0 to 2, right? So we identified this skeleton, that this is the only way in which the transitions can happen. So that are the state transitions. The third and the last steps is to identify the probability of transition. Okay. So this is the complete model specification for this problem. Okay. Okay, so now the next topic that we need to talk about is the n-step transition probabilities. Okay, so now we have defined the Markov chain. We understood that the Markov property, which is that Pij is that it only depends, the next state probability being in j only depends on the current state being I. It does not matter how you got to I. Okay, now if you really want to start using this model, we need to understand what happens in n steps. So this is only for one step. So we need to understand what happens in n steps. Okay, so what is the definition of this? So this is the definition. So this, what is this saying? The probability that you are at I, so this first part is still the initial state x0, at time 0 you are at I, okay, and at time n you have become j. So in basically n steps, what is the probability that you reach j given that you started off at I? Okay, so that is the concept that we want to define now. Now this has a very neat recursive structure. Okay, so now this is the state I. Okay, you can talk about what is the probability that you reach 1 to m in n minus 1 steps, and from that step you reach j in one step. Okay, so that's the idea. So from I to 1 in n minus 1 steps, there are multiple ways in which you can go. Okay, so you can account for all of these probabilities. Okay, that is r1i n minus 1. So this is the total probability of how to reach from I. Okay, so how to I, and the second one is 1. How to reach from I to 1 in n minus 1 steps. So this is the this probability. Similarly, for you can define ri1, this is ri2, and then rin. Okay, now so in order to reach j from this path, that is ri1 n minus 1 into p1j. Similarly, from 2 node you can go from ri2 n minus 1 into p2j. Like that you can define all of this. So the key recursion formula, we get this through this idea. Okay, so Rijn is like probability that you go to some other intermediate state k in n minus 1 steps, and from k to j in the one step you reach j. Okay, so that is the idea. So this, what is the underlying thing that we have made? What is the important observation that we have made? First of all, Rij, in order to really understand this, you have to understand what is the values for simple cases. So Rij of 0, okay, so that in 0 steps, what is the probability that you reach state j? So that will be 1 if I equal to j. So if I equal to j, then you are already at j, and in 0 steps you will remain at j, otherwise this is 0. Okay, similarly, another important thing that you should observe is Rij of 1. In one step, what is the probability from going from I to j? So this is nothing but Pij. All right. So these two are the underlying key assumptions. So this is the one step probability. Okay, so this is the key recursion. Now, if the initial state itself is random, now if you want to understand what is xn equal to j, this is not a recursive equation. Please don't get confused. This is not having any recursion. All this is saying is, in order to reach from I to j in n steps, first you have to be in I, and the probability of being in I is x naught of I. The probability that x naught is I. Okay, so the initial state, if it is random, what does that mean? So you have a distribution on the states, initial states. So x naught, for example, can be 1, it can be x naught, can be 2, and so on. So if you sum all of this, it will be 1. So suppose you have given a distribution like this on the initial state. What is the probability that in n states you will be in state j? Okay, so this is not a recursive thing. All right. So now we can also define this recursion in a different manner. Okay, so this is one. So let us look at a variation. Okay, in this variation, what you can have is like you are at I in one step. Okay, so this is time 0. Okay, in time 1, in one step you get to some states 1. Sometimes you may get to 2, right? And you can get to m. So what is the probability this happens? This is pi1, this is pi2, this is pim. All right. And from I to j, from 1 to j, you look at r1j n minus 1. Okay. So this way also you can define. Okay. This will be r2j n minus 1, like this. So the recursion here in this alternate way will be Rij of n will be summation, okay, k equal to 1 to m pik, okay, into r k j of n minus 1. Okay, it looks similar to this, but the whole mechanics in which it is defined is a different thing. So you can either use this or this depending upon which one you think will be easier when you solve it. Okay. So this is the idea. So let us try to use some of this in an example. Okay, so we will use the example which Sitsiklis gives. Okay, So now consider this example. There are two states, 1 and 2, and these are the state transitions. Okay, now let's try to fill up this table. Okay, so Rij, so remember what is this saying? So let me write that. Rij of n, what is that we are saying here? What is the probability that xn is equal to j given that x0, the starting state, is I? So basically you are asking the n step probability, transition probability. Okay, so one step transition probability is given in these things. So let us try to fill in these numbers. So if there are no steps, so you are starting at 1, what is the probability to remain at 1? In 0 steps, this is 1. Okay, so let me write it. I hope that, yeah, this is 1. So what if you are in 1, what's the probability that you get to 2 in 0 steps? That is never going to happen. So this is 0. So similarly, you can fill up these numbers. Alright. Now, what is the probability that in one step you get from 1 to 1? So that is this is this number right here. So this will be P11, and in that case it is actually 0.5. This will be in fact P12, this is also 0.5. Okay, then this is P21, P21 is 0.2. Okay, so from 2 to 1 in one step. Then finally P22 will be 0.8. Okay, so now when we want to suppose do R1 1 of 2, okay, so this one we have to understand. So we have to use the recursive formula. So we know how to look at R1 k of 1 and then pk1. So that's what we have to look at, right? So this is the recursive formula, and k will be 1 or 2. Okay, so this is the idea. So we have already R11 of 1, so that is over here, right? So from 1, what is the probability that you remain in 1? So that is here. So that will be P11. So this is 0.5, you remain in 0.5, this is 0.5, so 0.25, okay, plus R12, okay, from here you can get to 1. So what is the probability from 2 you get to 1? Okay, so that's 0.2. Okay, so now the total probability is 0.5, this 0.5 into 0.5 plus 0.5 into 0.2. So this is 0.5 into 0.7, which is 0.35. Okay, now if you want to answer R12 of 2, that is, you can use the same way like I have done, or you can do 1 minus R11 of 2. Okay, so at time 2 you can be either in state 1 or state 2. This one, starting from state 1, you can be either at state 1 or state 2. Okay, so either this happens or this happens. So that's why you can use the other way and you can get this. So this is 0.65. Alright. Now it turns out that if you run this like this for many things, it turns out that at time t equal to n equal to 100 in n time steps, this will be close to 2/7. This will be close to 5/7. Okay. Now you see what curious phenomena happens when you come to n equal to 101. So let us write that R11 of 101 is going to be, okay, R11 of 100. So in 100 steps you are in 1 into P11 plus R12 of 100 into P21. Okay, so let's do that. R11 of 100, we know that is 2/7 into, okay, P11. What is that? P11 is half. 0.5, we will write it as half, plus R12 of 100, that is given by 5/7 from the previous entry here in the table. Okay, and from here you want to get back. Okay, so that is 0.2. Okay, we will write it as 1/5. Okay, so now you can see when you do this math, so this actually this two becomes cancels, so this will remain at 2/7. So from 100 to 101 the probability didn't change. Okay, similarly it's happening like as though once you are in this state, you remain in this state. And another curious phenomena that happens if you do this calculation for even here, so these numbers also tend to be the same. Okay, it didn't. So here what is the difference between R21 and R11 of 100? R11 of 100 versus R21 of 100. Okay, so this is the probability that at 100 you are at state 1, but the starting point is different. Here the starting point was 1, here the starting point is 2. But in this example, it looks like it doesn't matter where you started. Okay, it seems to have come to some kind of a steady state. Okay, so basically this is this thing that you observe here. It seems like what is happening after the chain, the Markov chain. Okay, this is the Markov chain, right? The evolution, everything is happening through a Markov process. Okay, the system has settled into a steady state. Okay, that is one thing. See, what does that mean? From this to this there is not much change. That is the steady state. Okay, this is point number 1, and it does not depend upon where it started. Okay, this is point number 2. So there are first of all it settles or it converges into some numbers, and then it remains in that number. That is the steady state. Okay, and secondly, it also doesn't depend upon where it started. Okay, see, the steady state doesn't mean that at n equal to 100 the Markov chain stops transitioning. The transition probability is still happening with this, right? You see, we have done that computation here. It's still jumping around. But at n equal to 100, if you were to just look at the system at n equal to 100 and look at what's the chance that you are in state 1, that will be 2 by 7. And what's the chance that you are in state 2? You will be in 5 by 7. Okay, so this is what is meant by steady state. Alright, so now there is also some intuition here. Why is this 5 by 7 bigger? That's because, you know, if you see from 1 to 2, if you are in state 1, there is a good chance that you immediately move out to state 2. But in state 2, you tend to remain a little bit longer, and hence the steady state probability also reflects that 5 by 7 is a bigger number than 2 by 7. Okay, so this is a concept that is also quite intuitive. All right, so let's try to understand when these two things happen. What are the two things? The system settles into a steady state, which means that from one time step to next time step, the probability of being in a state doesn't change much. That is point number 1. Point number 2 is it does not also depend on where it started. Okay, so that is what we are interested in. When does this phenomena happen? Does it happen only for this problem? Okay, so that's the next question that we will attempt to answer. Now coming back to the two questions. So the first question is from n to n plus 1. Okay, does, like in the previous question, if you see the example that we just did, from n 100 to n 101, the probabilities didn't change much. Okay, so it's like, does it settle to something? Does the probability settle to something? And here is a counter example. So you look at 1, 2 and 3. So basically the first thing does not always happen. When does it happen like that? So if you look at this system, okay, once from let us say you start at 2. So what is that? So here x0 is equal to 2. Okay, so now when you are starting at 2, what will happen with certain probability? Okay, you will either go to state 1 or you will go to state 3. All right, and then in the next time step you are assured to come back to 2. So if you think about it a little bit, when n is equal to odd, like if from starting from 2, if n equal to 1, either you will be at 1 or you will be at 3. You will never be at state 2. Okay, so this probability is 0 for all n equal to odd. For n equal to even, you are starting at 2. Okay, so you have gone to some place. So at previous n minus 1, you are at some odd point, either 1 or 3. In the next step, you are bound to return to 2. So this will be 1. Okay, so if what does that mean? An example, let us say R22 of 1 million plus 1. Okay, this will be 0, and R22 of 1 million plus 2, this will be 1. Okay, so here when you have run for sufficiently long time, 2 by 7 remains 2 by 7. Okay, 5 by 7 remains 5 by 7. Alright, but here that is not happening. Even though we are starting from the same state for both of these systems, okay, at even and odd times there is always going to be a fluctuation. So this is something called as periodicity. So this Markov chain has the periodicity property. Okay, so this is something that prevents a Markov chain from settling into some convergence, settling into some fixed numbers. Okay, so this is a counter example. Okay, let us look at one more counter example for the two questions that we were answering. So first question was, does it converge to some steady state numbers? Okay, and second question is, does it depend on where it started? So first question we have given example, whenever there is a periodicity, it may not settle. Okay, so now let us try to look at the second aspect of this. Okay, so now the dependence on initial states. So the first state is first question that we looked in the periodicity. What we said is that if there is a periodic structure, then the numbers don't settle into some numbers. Now the second question is, can we remove the dependence on the initial state? Okay, if the Markov chain runs enough number of times, does it forget from where it started? Okay, so this answer unfortunately also is not no. It does depend on initial state. Here is an example below. Okay, so if you observe this Markov chain, once it is in state 1, it always remains in 1. Okay, no matter the n. So if you look at this, what's the probability that the state remains at 1 given that it started in 1? This is always going to be 1. Okay, now look at 3, 1. So let's say your system is at 3. What's the probability that it comes to 1? Okay, so but that is never happening, right? From 3 it either goes to 3 or goes to 4. From 4 it remains in 4 or comes back to 3. There is no way it goes to 2 and no way it goes to 1. So if it starts at 3, there is no chance of reaching 1. So this is 0. So similarly, if you look at what's the probability that the system reaches state 1 given that it's at state 2. Okay, so now from 2 it can remain in 2, it can go to 1, it can go to 3. Okay, so all these things can happen. Okay, so R to 1, if you really think about it, there is only 50% chance that if you start at 2 you will reach 1. Okay, because with 50% chance you go to 3 and never reach 1. So this is going to be 0.5. So this counter example clearly shows that initial states can be important for examples like this. Okay, so let us try to understand what is happening in this particular example in general. Okay, so once we get an idea of that, then we can see what prevents this from being independent of the steady state, initial state. What prevents it from being independent of the initial state. So in order to understand what happened in the previous example, why the system does not get independent from the initial state, we have to look at a example like this. So look at this example. So let us say this is called let's name these nodes 2, 3, 4, 5, okay, 6, 7, 8. Okay, so now there is a concept of a recurrent state. So what that means is, if you start from I, no matter where you go, you will always some way of returning to I. Okay, that means there is no chance that it will go to some state from where you can never return. Okay, so such a state is called a recurrent state. For example, if you are here starting at 1, okay, there is only way you can remain here is always 1. Okay, so what are the recurrent states? So state 1 is recurrent. Now similarly, if you look at 6, 7 and 8, from 6 it can go to 7, from 7 it can go to 8. But there is always a path to come back to 6. So 6 is also a recurrent state. Now whichever state from 6, wherever you go, those are also going to be recurrent states. So these are all different recurrent states. However, if you look at 2, 3, 4 or 5, okay, so there is a way from if 2, 3, 4 or 5, if it remains in these 4, it may just remain here. But from 2, 3, 4, 5, if it goes to 1, it will never come back to 2, 3, 4, 5. Okay, these are called transient states. So what are the examples of transient states? 2, 3, 4 and 5. Okay, so in a transient state, there is a possibility that you reach some point from which there is no coming back. All right. So yeah, and as xn, the probability for a transient state I, the probability that you are at state and you are at point I, this goes to 0 as n tends to infinity. Okay, that means I is visited only finite number of times. So these are all the variants of the same definition. All right, I hope this idea is clear. Why does the probability go to 0? Because eventually you are going to go to either state 6 or state 1. okay, and after that there is no coming back. Okay, so it's very small chance that even for very high n you remain in the system. Okay, and then as n increases, this probability reduces further and further. Okay, now if you look at this, there are two classes. From 1 you can always remain in 1, so this is one class. Okay, from 6, 7 and 8 you can go from each of this to each of the other states. Okay, those are called recurrent classes, but there is no communication between two different recurrent classes. Okay, so this is the thing here. Now in this initial state, dependence comes because there are two recurrent classes. Okay, if you reach one class, you can never reach the other class. So if you are in this class, you remain here. If you are in this class, you remain here. So if the system has more than one recurrent class, then it is possible that the dependence on initial state is there. Okay, so this is the concept that we wanted to understand and to arrive at. Okay, so I hope this is useful. All right, so let's stop here.